In this video, I will discuss Gauss Quadrature methods as numerical integration methods, which have kind of a different approach than the methods that we've covered so far. Before we start discussing what Gauss Quadrature rules are, let's take a brief look at what we've covered so far. And all the methods that we've seen, the rectangle, midpoint, trapezoid, and Simpson's rules, are categorized in the so-called Newton codes type of methods. And in such Newton codes methods, well, what do? Is first we pick a number of points, and we pick those points to say that, well, these are the points where we will evaluate the function in order to approximate its integral over a certain interval. And the amount of points depends on, well, that will depend on which kind of integration method that we're trying to use. The next step is that we approximate the function f of x on the interval where we want to integrate f over by an nth degree polynomial. And in these examples that you see over here, f is this black line. So the graph of f is this black line. And we want to integrate from x is minus 1 to x is 1. So a is minus 1 and b is 1. And by choosing a different n, so a different degree, a different, well, higher degree of the polynomial, which corresponds also to taking more and more points in the integration interval, so more collocation points where we evaluate the function, you see that we end up with different kind of approximating polynomials. Now, the good thing about these polynomials is that, well, f is probably a function that we can very hardly integrate, so otherwise we wouldn't need numerical integration. So this is very difficult to integrate, but polynomial functions are very easy to integrate. So you can easily give an analytical rule to integrate each of these polynomial functions. And in that case, well, we say that the integral of our original function can be approximated by the integral of the polynomial function that approximates that function f. So that is the kind of strategy that we're using here. And by picking different n, we end up with different methods, as I already mentioned. So if we take n is 0, that means that we only have one collocation point. And that collocation point can be, for instance, at the left-hand side of the interval, which corresponds to the left rectangle rule as depicted over here. Or it can be at the right-hand side, which would be the right rectangle rule, or at the middle, which would be the midpoint rule. And that's the rectangle rule. If we take 2 points at the edges of the interval, well, that's the trapezoid rule. If we take 3 points, so at the edges of the interval and at the midpoint, we approximate f with a quadratic polynomial over the interval, then doing this entire step would lead you to Simpson's 1/3 rule, and his 3 would be Simpson's 3/8 rule, and you could keep on adding more and more points in hopes that your approximating polynomial gets closer and closer to the actual function f of x, so to the black line. And if your polynomial, so the approximating polynomial, is closer to the function f, well, then also the area below that polynomial is more similar to the area below the function f. So you have a better approximation of the integral in that sense. However, when we keep on increasing the degree of such a polynomial by keeping the collocation points, so the points where we base this polynomial on, where we evaluate the function f, then we see that, well, starting from n is 0 here until, let's say, n is 4, the accuracy of the approximation gets better and better. So that's exactly what we want and what we would also expect from a first instance. But if we keep on increasing n to larger and larger values, we encounter what is called the Runge phenomenon. And the Runge phenomenon, the origins thereof are not so important, but the consequences are quite disastrous if you're trying to approximate a function and approximate its integral more precisely, in the fact that, well, at the end points, even though at the collocation points itself, you will get closer and closer and closer to the function f of x by definition, in between these collocation points, the approximating polynomial might start having these very large oscillations which deviate from this smooth function f that we're trying to approximate. And you can clearly see this for NS16. Here we have this bump on the left. We also have a small bump on the right. So this will give an error when we try to approximate the area below the black line by the area below the red line. And also here for NS24, it keeps getting worse and worse. The error here is actually really out of bounds. I think this goes down to -2 or -3. So you see that when we're adding more and more points for these evenly distributed collocation points, that we really start getting into trouble, and that this is not a sustainable way in order to try and increase the accuracy of your integration methods. Now, so far, well, all the points that we've chosen here, we say that, well, we take the endpoints and then we evenly distribute our points along the interval. So if we take 3 points, that's the point on the left, the point on the right, and the point in the middle. Where we took 4 points, well, we took the point on the left, the point on the right, and the other 2 points, such that these 3 subintervals are of equal size. However, well, this doesn't give us a lot of freedom, and maybe choosing a different collocation point, so not placing them in an equidistant fashion, but placing them in a slightly more intelligent way, could get rid of this of these oscillations that we're seeing over here. And an example of such good points that we could actually use instead of these equally distributed collocation points that are used in the Newton-Cotes methods are Gauss points. And I will just show you how these Gauss points look in the next slide. So here we see, and I'm not going to tell you just yet how we got these Gauss points, and we will come to that later in this video. But you see that by intelligently choosing the location of such points, they are not equidistant, as you can, for instance, see over here. For NS8, we have a much smaller spacing close to the edge than we have in the middle. So by in some way optimally distributing these points over the interval, we can get rid of these nasty oscillations that could be very harmful for our approximation of the integral. And these Gauss points, well, they will play an important role in the rest of this video on Gauss quadrature. So the idea is that we not only try to approximate the function with a polynomial. No, we will also try to find the optimal points in the interval where we can evaluate that function. And that is the whole idea behind Gauss quadrature rule. So Gauss quadrature, it's really a change of strategy. So again, just let me reiterate, Newton-Cotes methods, they fix the collocation points on the edges of the intervals, and then we just subdivide the interval based on equal subintervals. And then we approximate the function using a polynomial of degree n, and we hence approximate the integral as the integral of this polynomial that we can easily compute. Now in Gauss quadrature, we take a different approach. So what we actually do is we directly approximate the integral as a weighted sum of function evaluations, so the weights C1 to Cn. But most importantly here is that, well, for these Newton-Cotes methods, in the end, you also end up with a weighted sum of function intervals. The main difference here is that for Newton-Cotes methods, we fix these collocation points on equidistant intervals, whereas here we allow these points where we evaluate f to be free. And they will be part of the whole construction algorithm that we will use in order to attain a accuracy that is as high as possible. So it's important to state that here both the coefficients and the evaluation points are yet to be determined. So they are not predetermined here. Now, how do we determine those coefficients and the Gauss points, x1 to xn? So this is in total 2n degrees of freedom. Well, what we do is, we state some rules that we want to integrate polynomials up to a degree as high as possible. And using 2n points, well, this means that we will have as much degrees of freedom such that we will be able to integrate polynomials up to a degree of 2n minus 1 exactly. And we will see how this works in the next slides. So again, reiterating here, this is the whole idea of Gauss quadrature. So we directly approximate this integral of f with a weighted sum of function evaluations at these Gauss points. We determine these Gauss points and weights by requiring that polynomials up to a degree of 2n minus 1. So for n Gauss points, we want to be able to integrate polynomials up to a degree of 2n minus 1. Exactly. Also important is that, well, in this definition of how we find the Gauss points and the Gauss weights, that there is no real mention of the function f that we're trying to approximate. And indeed, the points and the weights in Gauss quadrature will be independent of the function f of x that we try to integrate, or that we try to approximate the integral of, to be more precise. Also, the evaluation points x1 to xn, well, in the standard way of writing it like this, well, the evaluation points are obviously dependent on a and b. They will be in the interval from a to b where we try to integrate this function. However, we try to make this into a standardized method for finding these Gauss points. So we normalize this interval AB to be from -1 to 1, such that these Gauss points x1 to xn are all included in this interval from -1 to 1. And this is without loss of generality, as you will see later, because we can easily transform this problem from -1 to 1 to any interval that you desire, where a and b are not equal to -1 and 1. But more on that will come later. So let's look at an example, because that will be very illustrative in how these Gauss quadrature rules actually work. So we want to find the weights and points, and we will make a single point Gauss quadrature rule. So this means that, well, we only have one term here. So we evaluate the function f at one point x1, which will be between -1 and 1. So that's this standardized interval that I mentioned in the previous slides. That's what we will do. And what we need to do is we need to determine this coefficient, so the weight and the Gauss point x1, by enforcing that the method is exact. So it will give exact integrals for polynomials of degree up to 2n minus 1. 2n minus 1 here is 1. So that means that we want an exact integration rule for polynomials of degree 0, which are just constants, and polynomials of degree 1, which are straight lines. So this will give us two rules, and from those two rules we will be able to determine both C1 and X1. And I will show you how this works. So first, let's say that we want to look at polynomials of degree 0. and a polynomial of degree 0 is simply a constant. And here I set this constant to be equal to 1. So if f of x were a constant, I choose it here equal to 1, but you would get exactly the same conclusions if you choose a different constant. So we just plug in this f of x here, and then we say that, well, this approximation should be exact for that constant function f of x. So we can evaluate our Gauss quadrature rule. So this ansatz, we can try to evaluate it now for this f of x is equal to 1. So the left-hand side first. So the integral from -1 to 1 of f of x, well, that's the integral from -1 to 1 of 1, because we said this is a polynomial of degree 0. The integral of a constant, we can throw out the constant, and then this integral, well, it's just the width of the integration interval, so that is equal to 2. So the left-hand side here that we find is equal to 2. What is the right-hand side equal to? So the right-hand side, that is c1, an unknown constant at this point, times the function, this function in this case a polynomial of degree 0, evaluated at an unknown Gauss point that we still do not know. However, if this is a constant, well, there is no x in the right hand, there is no x in this function here. So f of x1 is equal to 1, and c1 times f of x1 is simply equal to c1. Now, we want that both of these are equal to each other, because this is our whole idea of constructing this Gauss quadrature rule. So we find that c1 is equal to 2. So by this first condition, we already found a value for the weight in the Gauss quadrature rule. Now, we do not only want to say that our Gauss quadrature rule has to be exact for constant functions. No, we also want first degree polynomials, which are lines. So a first degree polynomial, for instance, this simple first degree polynomial f of x is equal to x. And again, you can plug in any first degree polynomial here that you want. You could do 2x, 4x plus 1, however you want, but this will give you the same conclusions. So we just do this for this most simple one for illustration purposes. And we again follow the same procedure that we did over here. So we evaluate the left-hand side of this approximation. And the left-hand side, well, again, integrate f of x from -1 to 1, where f of x is equal to x. And you can work this out. Well, the integral of this is x squared over 2. And x squared over 2 evaluated at 1 and -1 is the same, so this is 0. It's also because x is an odd function. Its integral over an equal integration interval from -1 to 1 will always be 0. Okay, so the left-hand side is 0. Well, what about the right-hand side? So the right-hand side, that is c1 times f evaluated at x1. F evaluated at x1 is simply equal to x1, so this will be c1 x1. And we already know that c1 is equal to 2. So we find that the right-hand side is equal to 2 times x1. Now, since we want this approximation to be exact for these kind of polynomials, well, the right-hand side, 2 times x1, should be equal to the left-hand side, which is 0. And that can only happen if x1 is equal to 0. So we have found our Gauss quadrature rule because we have determined both the weight c1, which is 2, and the Gauss point x1, which is 0. So the one-point Gauss quadrature rule for any function, and this is not only for polynomial functions, for any function will be the following, that we approximate this integral between -1 and 1 by twice the function evaluated at x is 0. And for polynomials of degree 0 and degree 1, this will be an exact equality. For other functions, this will only be an approximation. And how good this approximation is, well, we will look at that a bit later. So in the previous slide, we discussed finding the weights for n is equal to 1. Now let's take a look at what happens when we start adding more points. And you will see that, well, although the strategy is completely the same, starting to add more and more points, well, it makes finding the weights and the Gauss points a lot more complicated though. But we can follow the same procedure. So we want that this integration is exact for polynomials up to a degree of 2 times n minus 1. So that will be polynomials of degree 0 or constants, polynomials of degree 1 or lines, polynomials of degree 2 or quadratic functions, and finally polynomials of the degree 3, so cubic polynomials. So let's start out with a polynomial of degree 0. That's a constant. This is completely the same as we did in the previous slide. So the left-hand side, the integral of a constant of 1, from minus 1 to 1, that's simply equal to 2. And for the right-hand side, well, we simply evaluate this right-hand side for a constant function, and you see that we end up with simply c1 plus c2. We want this to be exact, so c1 plus c2 has to be equal to 2, and that is our first condition that we find over here. And so you see that this doesn't really already give us a clear, let's say, single coefficient. No, this is still an equation. We need more equations to determine C1 or C2. And in the previous case, well, we already got the first coefficient C1 already, but this is already a bit more complicated. So we have here an equation between C1 and C2. So let's take a look at the higher degrees. So for a first degree polynomial or a line, we find, well, f of x is x, simply equal to what we did in the previous slide. Left-hand side is equal to 0, so that's also the same as what we did in the previous slide. For the right-hand side, well, yeah, this is not very complicated, so we just substitute the x1 into this function f of x is x, and you find that the right-hand side is equal to c1 x1 plus c2 times x2. We demand that this is an exact approximation, so the right-hand side should be equal to the left-hand side, and we find another condition that c1 x1 plus c2 x2 is equal to 0. Continuing for the second degree polynomial, we just take this quadratic term over here. We integrate this from minus 1 to 1, plug in f of x is x squared in here. The integral of x squared, well, that is x cubed over 3, evaluated at 1 and minus 1. So you end up with 2 over 3 for this integral. And again, simply plugging in x1 and x2 into this f of x will give you this thing on the right-hand side. Again, we say, well, these two things have to be equal, which gives us another equation. And we can follow the same procedure to get the third degree, and this will give us yet another equation. So now we see that here we have 4 equations, and we have also 4 unknowns. So the unknowns are C1 and C2, and X1 and X2. So we have 4 equations, 4 unknowns. Sadly, these equations are nonlinear. So if they were linear equations, well, we could solve them using any technique from linear algebra, but they are nonlinear equations. Quite often these are not solvable by hand. They might have multiple solutions, so there could come a lot of problems in there. You could solve this numerically, and that would actually give you the same solution as we will try to find now by hand. So in order to find such an equation, find at least one solution of this set of equations by hand, well, we can impose another condition. And that is, well, let's try to find a solution to these equations which holds symmetry. So maybe we can find, evaluation points x1 and x2, so Gauss points, which are symmetric around the axis 0 points. So in other words, let's hope that we find a solution where x2 is equal to minus x1. And then you can substitute that into these equations, and we kind of eliminated one of the unknowns. And we see here, well, these are still nonlinear equations, but we can solve them because you can factor out x1 out of, let's say, this second equation. You can factor out x1 out of this equation, and then you can start dividing these equations by each other. And you can try this yourself, but this will lead you to finding a solution by hand. The entire procedure is not so important here. I just wanted to show you that it is possible in some cases to solve these things by hand if you, for instance, impose an extra condition that you would like to have symmetry. It would also have been possible that this would have given us an inconsistent system of equations, and then we would have to start over. But it turns out that if we impose this symmetry, well, we can solve these equations, and the solution is as follows. So the solution to these equations, well, it is that C1 and C2 are both equal to 1. And we find the Gauss points to be equal to minus 1 over square root of 3 and 1 over square root of 3. So this allows us to plug this into our Gauss rule over here. And then we find that this is the Gauss Quadrature rule for 2 Gauss points. So we can use, well, if we want to integrate a function between x is minus 1 and x is equal to 1, all we have to do is, well, we evaluate that function at x is minus 1 over square root of 3 and add to that the function evaluated at 1 over square root of 3. And this turns out to be an exact integration for polynomials up to a degree of 3. It will be an approximation for higher order polynomial functions and also for non-polynomial functions. It will be an approximation, for instance, exponential or sinusoidal functions. And we will actually try that in a moment. Now you can keep on doing this by adding more and more points. It doesn't really make sense to go into much more detail on how to on actually finding these points. The overall strategy is always the same. It's also important that, well, in this derivation that we did of these points, the actual function f of x that we want to integrate didn't really show up there. So if we want to approximate a cosine function, this doesn't affect the weights or the Gauss points. Whether it's a cosine function or an exponential function or a fifth order polynomial function, we can still use the same Gauss weights and Gauss points. And for this, well, this means that we can tabulate these weights and the Gauss points, and that's also what you find on the internet or in your textbook. I think you have them in your textbook up until, let's say, four or five Gauss points. And then you can easily just, well, plug this into your Gauss rule, evaluate your function at those Gauss points, use the corresponding weights, and that will give you an approximation for the integral of that function between minus 1 and 1. Simple as that. Now, I already mentioned quite a lot of times, you are using these Gauss Quadrature rules. Well, we build these rules for an integration interval from minus 1 to 1 because this allows us to tabulate those Gauss weights for that specific interval. But most of the time, you actually want to integrate your function over a certain interval over which you have no control. So in one of these examples that we looked at earlier, this decelerating plane, well, we had to integrate that function from v is equal to 40 to v is equal to 93. So in that case, well, you don't want to integrate over minus 1 to 1. Now, fortunately, we can do kind of a substitution such that our desired situation for a general a and b that we can still use these Gauss quadrature rules for functions between -1 and 1 using a smart substitution. And so we basically have to transform this interval from -1 to 1 onto this interval which we are actually faced with from A to B. Now, how do we do this? Well, we basically just have to transform it. So the first thing you do to make this -1 to 1 interval similar to this A to B interval is to, let's say, stretch it to have the same width as the AB interval. So in order to do that, well, here we start with this, let's call this not x, but we call this an auxiliary variable t. And let's say that we introduce another auxiliary variable s that we just multiply such that the width of s is equal to the width of AB. And that's what we have over here. So you just multiply with the half width of this interval over here. And then this will have a width of b minus a. So you see that it's wide enough now, but it's not at the correct location yet. Now, in order to find the correct location, well, this is centered around 0. And this interval is centered around a plus b divided by 2. So all we have to do is, well, in order to get x from s, well, we need to add this midpoint to this interval, just to translate it up into the point that these two coincide. So we can write x as s plus this shift of a plus b over 2, or if we plug in our initial, let's say, variable, which is from -1 to 1, into s over here, we have the relationship that we have to transform this variable t with in order to come up with x, such that if we integrate f from a to b, this corresponds to integrating the same function f from -1 to 1. And this is basically just a substitution that you're doing. And it's also similar to substitution when you're doing an analytical integration. So this means, well, if we then do this, well, we want to integrate this function f of x, which we do not know how to do this well, but we can integrate this function f as a function of t between -1 and 1, because for that we have these quadrature rules. And then using this substitution, well, you can find out that dx is b minus a over 2 dt. So that's where this b minus a over 2 comes from. And we just evaluate f not at t or not at x, but we evaluate it at t times b minus a over 2 plus a plus b over 2. So this is what I just did here, is just a substitution from x to t. And that's also how you solve some integrals. Now, the whole idea is that now we end up with a function between -1 and 1, and we can use these Gauss quadrature rules. So an example for such a Gauss quadrature rule for n is 1, and we already found that for n is 1, the Gauss quadrature rule on the interval from -1 to 1 is 2 times f evaluated at 0. And we can then transform this to a general interval from a to b. So we know that the weight is equal to 2, the Gauss point is equal to 0. So if we plug that in here, well, the Gauss point is 0, so t is equal to 0. So we just evaluate f at a plus b over 2. And the weight that we use to approximate this integral is 2, so we just added 2 over here. And this b minus a over 2 is just copied from this prefactor that we have over here. So working this out a bit, we see that the single point Gauss quadrature rule applied to a function on an interval from a to b, well, that will be b minus a times f evaluated at a plus b over 2. And we already saw this actually, because this is exactly the midpoint rule. So what this shows us is that the Gauss Quadrature rule for one Gauss point corresponds exactly to the midpoint rule. Just a brief recap of what I said in the previous slide. So if we want to integrate a function f of x from -1 to 1 using Gauss Quadrature, this comes down to a weighted sum with weights c1 and Gauss points x1 to xn, which are situated in the interval from -1 to 1. If we want to use the same Gauss Quadrature rules for a general interval from a to b, well, we need to add this prefactor over here, b minus a over 2, which kind of deals with the fact that the width of AB is not per se the same as the width of -1 to 1, which has a width of 2. So that's this factor over here. The weights still stay the same, but the Gauss points are modified. So they are rescaled also with this new width of the interval from A to B, and they are shifted such that they have a center point a plus b over 2 and not a center point of 0. So this will give you these modified Gauss points, and let's call them psi, which lie in the interval from A to B. And for this whole general idea from A and B, this might be very abstract at this point, but it will become much more clear when we apply this to an example. And such an example is what we see in this slide over here. So we want to use Gauss Quadrature rule to compute the integral from 1 to 3, so x is 1 to x is 3, of f of x for these two functions. So first for a fifth order polynomial function, and then for a sinusoidal function. Now, we see that we have an interval from 1 to 3, so that's not the same as this standard interval from -1 to 1. So let's take a look at how these substitution rules work when we apply them, in this case, for a is 1 and b is 3. So we just plug that in to this equation from the previous slides, and we see that this prefactor, so that's 3 minus 1 over 2, well, that ends up to be 1 in this case. So the width of the interval from 1 to 3 is the same as the width of the interval from -1 to 1. So this actually drops out, this rescaling that we have to do. Also, the rescaling of t drops out, but we simply have to shift the Gauss points that we would find from the table, which are designed to be between -1 and 1. We just have to shift them to the right with 2, such that they are between 1 and 3. And this is a practical example of how this can easily be, how such Gauss points can easily be used for intervals not between -1 and 1. So in this case, we would just have to add 2 to the Gauss points. Now, let's start with function a. So function a, well, that's a polynomial function. Polynomial functions, as we've mentioned many times in this lecture, are easy to integrate. You can check this for yourself, but it turns out that the exact value of this integral for this polynomial function is equal to 506. So that's the true value, and now we can try to approximate this true value of the integral with these Gauss Quadrature rules and see what this means for the accuracy. So what we do is, well, we approximate this integral with this weighted sum of coefficients times Gauss points, where these Gauss points are shifted with this distance of 2. And we use a sum of n terms. And I show this to you in the next slide in a MATLAB demo. So let's try to approximate the numerical integral of this polynomial function from a is equal to 1 to b is equal to 3 using Gauss Quadrature. And in Gauss Quadrature, we know that what we need to do is we need to compute a weighted sum of f evaluated at n Gauss points multiplied with n corresponding Gauss weights. So the only thing that is left for us to do in order to be able to compute this weighted sum is to find the Gauss points and Gauss weights for a desired amount n. And we already saw how to do this. We have to specify that we want to be able to integrate 2 times n minus 1 polynomials exactly, polynomials of the degree up to 2 times n minus 1, and we saw how to do that analytically in the slides. But it also turns out that this gets more and more complicated and involved as we increase n. So we really want the computer to do this for us, actually. Now, to the best of my knowledge, it actually turns out that MATLAB does not have a simple function which returns these Gauss weights and Gauss points to you in an easy way. So what we can then do is we can either try to program that ourselves or look on the internet whether anyone else has implemented such a function for us and whether we can use that function for our purposes. So let's give that a try. So I will open Google here and let's take a look at MATLAB Gauss Quadrature and see whether we can find something. So we see that the first link that pops up is titled Legendre-Gauss Quadrature Weights and Nodes. And Legendre-Gauss is a specific type of Gauss quadrature. And let's investigate it a bit further. So what we see here, well, this is a simple script producing Legendre-Gauss weights and nodes for computing definite integral of a continuous function on some interval AB. So this is the MATLAB file exchange, so anyone can upload functions to this platform. Here we have the description, so this seems to be what we want. And we also see that this has been rated. It has a quite high rating, so that makes sense. This is probably a good function. Now we can try to download this function. But you see you have to sign in, so if you want to circumvent that, you can just click on functions and then you get the files here. And we see that it's only this function. So we can simply copy and paste that into our MATLAB, into a new script. And let me just paste it right here. And I'll save it. And let's just, for clarity, give it the correct name, LGWT. So let's investigate this function. And we see that it has 3 inputs. So the first input, n, well, that is the amount of Legendre-Gauss points that we want in our evaluation. We have a, which is a starting point of the integration interval, and b, which is the end point of the integration interval. And those are, well, user-defined parameters. What comes out is a vector x corresponding to the Gauss points and a vector w corresponding to the weights associated with those Gauss points x. So this seems to be very suited for the task, and it says, well, you can compute the definite integral using simply a sum of f evaluated at the points x multiplied with the corresponding weights. So let's give this a try. Let's make a script where we try to make this numerical integration of the polynomial function. So this is a demo script for the numerical integration by Gauss quadrature of a function, and this function is f of x is 6 times x to the power 5, 6x to the power 5, minus 5 times x to the power 4, plus 3 times x squared, minus 2 times x plus 1. That's the function that we have. And we want to integrate from a is equal to 1 to b is equal to 3. So that is in words what we want to do. So now let's start programming this. So well, let's set up some parameters first. So we know that the start point of the interval is 1, the end point of the interval is 3. Okay, let's define the function f. So it's a function of x. When I can simply just copy this such that I don't have to type it all again. What I do have to take care of is, since x can be a vector and we want element-wise operation, so element-wise exponentiation here, I should add these dots. And this should be fine for the function f. So we already have defined the endpoints of the integral, the function f. So the only thing that's left for us to do is to, well, first compute the Gauss points and weights. And then second, we approximate the integral by a weighted sum of f evaluated at the Gauss points with these weights. Okay, so let's give this a try. So the hard part is computing the Gauss points and weights. Well, for that we have our function LGWT. And the inputs are, well, the amount of Gauss points that we have. And let's start with one Gauss point and the integration bounds A and B. And what comes out will be the Gauss points and the corresponding weights. And let's just call them C like we did in the slides. C for coefficient, or you can use W for weight. Doesn't really matter. So let's give this a go. We can already run this and take a look at what the Gauss point and the Gauss weight corresponds to if we want only one point. And we already saw in the slides that the Gauss Quadrature rule for a single Gauss point corresponds to the midpoint rule. And we see here indeed, well, the output, this Gauss point, is equal to 2, which is the midpoint between A is 1 and B is 3. And also note that because we can specify A and B here, these Gauss weights are already shifted and rescaled to the specific integration interval A and B. So these are not these standardized Gauss weights between -1 and 1. No, they are already shifted. So we do not need to do this transformation that we saw in the previous slides. So we can just evaluate f directly at these Gauss points for this integration bounds. So we see that indeed, well, we come up with the midpoint rule. The coefficient is equal to 2, and the Gauss point is equal to the midpoint between A and B, which is also equal to 2 here. Now the approximation of the integral will be f evaluated at the Gauss point, which in this case is only one point, but it could be multiple points, so this could be a vector, then multiplied with the Gauss weights, and we take the sum of all these values. And in this case, well, this will only be one number because we only have one point, but let's take a look at what happens with multiple Gauss points later. So I will run this now, and we see that the outcome here is 242 for the Gauss Quadrature approximation of the integral. Now actually you can compute the integral of this polynomial function by hand. It's a polynomial function. You can analytically integrate this, and the analytical solution, you can actually find this, is 506. So we see that we are quite far off from the value that we really want over here. Okay. Now let's see what happens when we start adding more Gauss points. So let's make this into a loop. So let's parameterize n, and let's go from 1 to 4, and we want n Gauss points, and we just output this I to the command window as well. Let's indent and run. And we see, well, we have 4 outputs in this case. So this is the midpoint rule, or the Gauss Quadrature rule for one Gauss point. We see that starting from 2 Gauss points, we already have uh, something which is quite close to the analytical solution. And starting from 3 Gauss points and more, we have the exact solution. Why is this? This is actually by construction, because we know that for n Gauss points, the Gauss Quadrature rule allows you to integrate polynomial functions up to a degree of 2 times n minus 1. So we see that we have basically perfect accuracy starting from n is equal to 3. Now we can also easily do this for other functions by changing this definition of the function f over here, and that allows you to easily compute Gauss quadrature rules for various types of functions. So in this slide, you see a short recap of the results that we found from the MATLAB demo. Where for a different amount of Gauss points, we approximated the integral of this polynomial. And we see that, well, from n is 3, actually, we are guaranteed that by construction, we should get the exact value of the true integral, so the exact value of 506. And that is also the case. So for n is 3 or n is 4 or more and more, adding more and more terms, that we're guaranteed to have the exact solution. And already for n is 2, we are relatively close. So the error here is about 10. Now you have to keep in mind that the amount of function evaluations is extremely low here. So this is only 2 function evaluations, and we're pretty close to the exact solution. And starting from 3 function evaluations, well, we have the exact integral, the exact value of the integral for this 5th order polynomial. Now, let's take a look at a non-polynomial function. So for instance, a sine function. Because for polynomial function, well, we have this guarantee that by construction, Gauss quadrature methods are very, very accurate. But this is not the case for general functions. And we should hope that, well, the Gauss methods also work very well for them. So let's investigate. Now we want to approximate the integral of the sine function between 1 and 3. And again, we can compute this analytically. So the antiderivative of the sine function is minus a cosine function. And you can compute this thing. It's about 1.5303, let's say. Computing this with Gauss quadrature, we see that, well, given the limited amount of function evaluations, so for example here for 4 function evaluations, we can already approximate this integral up till, let's say, 7 accurate numerical digits. And that's quite impressive, I'd say. So also for non-polynomial functions, these Gauss quadrature rules seem to work quite well. Let's also compare this Gauss quadrature method to the methods that we saw earlier in this video lecture. So to these Newton-Cotes type methods, rectangle, midpoint, trapezoid, and Simpson. I'm not going to go too much into the details, but it's very important here to see that, well, from three Gauss points onwards, we already have the exact, well, at least until 4 digits after the decimal separator exactly around it, we have the exact correspondence to the value over here. And this is only for 3 function evaluations. So compare this to, for example, the rectangle rule, where for 100,000 function evaluations, we didn't even get this kind of accuracy, but here we already have it for 3 function evaluations. So this really hints to us that these Gauss quadrature rules are very, very accurate. Also comparing them to the Simpson methods here, they are exact, well, in this case for starting from 10 function evaluations. So they seem to be at least comparable in accuracy to these Simpson's methods. A more detailed analysis of the errors will come in video for section 9.8, but the overall conclusion here is that with a very limited amount of function evaluations, these Gauss quadrature rules seem to be able to approximate the integrals up to a very high accuracy. So summarizing the Gauss quadrature rules, well, the idea is that we directly approximate this integral with a weighted sum of function evaluations. Both the weights and the points where we evaluate the function, or which are called Gauss points, are essentially free. And they are chosen in such a way that polynomials up to a degree of 2n minus 1 are integrated exactly. These Gauss weights and Gauss points are independent of the function f itself, which allows them to be tabulated and pre-computed for you. And we also discussed how to do this by hand, but we saw that this gets quite a lot more complicated when we add more and more Gauss points. I showed you that they are really accurate and efficient for polynomials, and that is actually the case because by construction they are exact for polynomials up to a certain degree. But also for non-polynomial functions, they seem to be very accurate methods of integration. And we will take a look into the error a bit later, but the general conclusion is that these Gauss quadrature methods seem to be a very accurate way of approximating integrals numerically.